Hello and welcome to another step towards our solving initial value problems using the Laplace transformations. In this presentation, we're going to discuss what is known as the Exponential Shift Theorem. By the end of this presentation, you should actually make some good sense of the writing you are seeing in this front page here. And that talks to our outcomes for this presentation. By the end of this presentation, you should be able to apply the exponential shift theorem to determine the Laplace transformation of time functions. You must also be able to use the combination of the linearity property of the Laplace transformation and the exponential shift theorem to determine Laplace transformations and be able to solve some problems. So let's start this way. We've seen this before. Given as time signal x of t equals to t, we computed the Laplace transformation definition. We actually concluded that t transforms to 1 over s squared as its Laplace transform, and in the opposite direction 1 over s squared transforms to a time domain signal, which is x equals to t. Now, in this presentation, we are focusing on that problem with some kind of modification of the signal. For example, let's say we've got TUT, emphasizing there that we're dealing with a causal signal, and suppose that this signal is multiplied by e tau t. You can see the same signal multiplied by that. We know already that this one has got this Laplace transform. Now our question is, how would we determine the Laplace transform of a signal of this nature, which is actually a result of this one multiplied by an exponential function. Now, looking at it in general, let's suppose that x of t has got a Laplace transform which is x of x, and now our task is to say, knowing the Laplace transform of x of t, how would you get the transform of e to the power tau t multiplied by x of t? At this point, we're going to evoke the definition of Laplace transform, which we all know is given in this form. In this case now, we are trying to make sense of the Laplace transform of this signal, which is given here and by definition. So taking this to expressing this integral as a limit, using a limit, we can see that our expressing the limit, we have t tend to infinity, then our definite integral from 0 to the parameter t. And now at the same time here, we apply rules of exponent to these exponential factors, and we're acting the exponents there and getting tau t minus st. And then moving forward, we can actually reorganize our exponent here by simply taking a common factor t in these two, and also taking a common factor minus 1 and ending up with minus s in brackets minus tau multiplied by t. That's what we have got here. And then we consider taking s minus t equals to sigma. Then we immediately replace this difference here by sigma. Then we've got here a definition of the Laplace transform of x of t, e to the power minus sigma. If you can look at this carefully, you can see this is the usual definition of the Laplace transform, except that s, the usual s there, has been replaced by sigma, which is equal to that. So we're just using here sigma as a helping variable. And then moving forward, we see that what we've got here actually defines a Laplace transform of x with respect to sigma. And that is not strange, because this is just a change of the parameter, which was s, we just changed to sigma, because we've taken sigma to be equal to this difference. So already we've defined the Laplace transform in terms of sigma, but we can substitute back to this, and then we can now get this expression written, instead of being x of sigma, be x of s minus tau, simply substituting sigma by s minus tau. And then what we're actually seeing here is that we're just replacing these two. So it's just the same expression, except that here we've got the Laplace transform expressed in terms of sigma, and here the Laplace transform expressed in terms of s and the tau, which is actually the scaling factor here in the exponential function, which is multiplying x of t. So what we're being told here is simply that the Laplace transform of such a signal will look exactly like the same Laplace transform of our x of t, which you started with, except that it is going to be expressed in terms of s minus tau. And you must be careful not where that tau is coming from, and the tau started here as a scaling factor to the independent variable here of the exponential function multiplying x of t. I hope that is clear. And then what we are seeing actually is that, let's say with this signal, we know its Laplace transform is this. What we've been just told by the theorem is that if you've got a signal given this way, the Laplace transform being x of s, if we multiply the x of t by e to the power minus tau t, tau here being the scaling factor there, we then get the same Laplace transform expressed in terms of s minus tau. So now the question is, now if you've got t ut being 1 over s squared, the Laplace transform, the question is, what is the Laplace transform of e tau t multiplied by t ut? That is our question there. But from this discussion, it simply says we take exactly the same transform and express it in terms of s minus tau, which we get as follows. If you look at this expression and that expression, is the same rational expression with the denominator squared, and here the same rational expression with the denominator squared, but here comes in terms of s, and here it comes in terms of s shifted by tau. So which means if you multiply a signal in a time domain by an exponential function, then the transform will come as a kind of a shifted function, horizontal shifted function in the frequency domain. From here, I think you have to look at some examples to make more sense of what we're talking about here. But before looking at examples, we see now that we can add another row in this table of transforms, just expressing that property, which is the exponential shift theorem. So that if we know the transform of s, and then we get that x multiplied by e sigma tau, then the Laplace transform will look like x of s minus sigma. Looking at examples, we've got our first example here, which is actually a multiple of t multiplied by e to the power 2t. So whether we take the translation in terms of sigma or tau is the same thing. Let's say now here in this case, we can see that in this term here, in this expression, our tau is actually 2. And then when we come to this one, we've got a sum of two signals. And in this first term here, we've got t squared, but it's multiplied by e to the power minus t, which means in that case here, our tau will be equals to minus 1. And in this term, like in the previous exercise, we've got tau equals to 2. So we can see that here, we're going to, both exercises are going to use the linearity property of the Laplace transform together with the exponential shift theorem. So now let's discuss the example further. So we'll be in this case now having our table of transform, and then what we're focusing here, we're focusing on the signal t ut, whose transform we know is 1 over s squared. But we also got here minus 0.5 multiplying that, which means we're going to need linear property. So when we take Laplace transform of minus 0.5 t e to the power 2t ut, then we're simply going to apply our linear property by taking out the constant minus 0.5, and then we remain with the Laplace transform of t e to t ut. What we're being told here is simply that the Laplace transform of this will be a Laplace transform will got exactly the same shape, but in terms of s minus tau or s minus sigma. So what we're going to have here is minus 0.5 1 over a denominator which is squared. In this case here, our tau or sigma is 2. So we're going to have here s minus 2, and that we're simply going to write as minus 0.5 over s minus 2 squared. Then we'll have done there. Now moving to the next example. Now we notice here now we've got a sum of the two. We'll simply apply the same property in each summand and apply the linear property. So we've got here Laplace transform of 3t squared e to the power minus t plus 5 e to the power 2t, all in brackets, multiplied by ut. Recall that we're dealing with the causal signal. And then applying the linear property, we will simply get now 3 Laplace transform of t squared e to the power minus t multiplied by ut, distributing ut as a common factor, plus 5 Laplace transform of e 2t multiplied by 1, because e to the power 2t alone is simply 1 times e to the power 2t. I'm looking at that way so that I can now look at this as a product of the exponential function and the unit step function there, which actually going to give me this type of a Laplace transform. But because of the exponential shift here, it's going to be in terms of my s minus 2. And then here we've got our tau equals to minus 1. Now if we were to write now this as s minus 1, because our tau is minus 1, then we would simply get this as s plus 1. So now we've got to look at the Laplace transform of a t squared, which is this one, which gives us 2 factorial over s cubed. So what we're going to have here, we're going to have 3 multiplied by 1 over a cubed expression. Actually, this is a square, so we've got here 2 factorial, which is 2. And then there's a minus 1 there. We get that as s plus 1 cubed. That will be the Laplace transform of this part here. Plus 5. In this case here, we've got the unit step function here. Actually, I've got to multiply here by ut, and then that gives us 1 over s. And then because of this exponential theorem, then we're going to write that in terms of s minus 2, this 2 here. So we're going to write this 5 times 1 over s minus 2, and then we just simply reorganize that and give our final answer as 6 over s plus 1 cubed, multiplying this and that, plus 5 over s minus 2. I hope you understand these denominators are basically written in terms of the scaling factors of t in this exponent function here. This is 2, then the Laplace transform of this part is written as in terms of s minus 2. And here you've got the scaling factor being minus 1, and then this part is written in terms of s minus 1, which is s minus 1. Then there you would have then applied properly your inherent property, which you applied here, and the exponential shift theorem, which we've just discussed. So going forward, I would urge you to look at a number of examples involving these two properties for practice. We are still in preparation for the discussion of our method of solving initial value problems using the Laplace transform. So for your practice, I leave you the following exercises, and you will see that in some exercises you will need to do some kind of simplification before you can make sense of what you are supposed to do in order to give the Laplace transform of a given function. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Sugasfani Msipa.